This video covers section 1 and the first part of section 2 of chapter 6 about probabilities. We'll talk about definition and notation for probabilities, the basic rules of probabilities. We'll talk about independence and sampling with and without replacement, and we'll introduce the general OR rule. In the 4 stages of statistics, we're talking about probability, and in particular, finding probabilities. To put this in perspective, the way that we will use probability in the context of statistics is that we'll assume that we know something about a population, and we'll ask the question, what should our samples look like? That is a question for probability. Here's some definitions. Statistics is the science of producing, summarizing, and drawing conclusions from data. When it comes to samples, statistics talks about how to summarize sample data. Probability is the science that deals with random behavior. When we talk about probability, we talk about the chance of something happening. Let's talk about what we mean by that. There are 3 ways to determine the probability of some event. Let's look at some background. The probability of a randomly chosen card being a heart is 0.25. The probability of a randomly chosen student in a class getting an A is 0.25, according to the professor. The probability of some candidate being elected, according to an editorial, is 0.25. Now, all these 0.25s are the same, but the question is, are these probabilities all determined in the same way? Well, the answer is no. Let's look more closely. Probability of an event is defined as the chance of that event occurring, which is determined as either the proportion of equally likely outcomes that make up the event, or it could be the proportion of outcomes observed in the long run, or it could be a number that's simply assigned subjectively or intuitively. So looking back at our examples, when we talked about the probability of a randomly chosen card being a heart, the probability of a randomly chosen student getting an A, and the probability of a candidate being elected, which of the 3 methods for assigning probabilities were used for each? For the first one, since we know everything that we want to know about the deck of cards, we know that each card is equally likely to be chosen. This 0.25 is a proportion of equally likely outcomes. In this case, there are 13 hearts and 52 possible cards, so the probability is 0.25. For the student getting an A, here we have a professor who knows that, in general, over the course of his or her career, that professor's students get A's about 25% of the time. So looking at those long-run outcomes, the professor can estimate that the probability of a randomly chosen student getting an A is about 0.25. Finally, because the election of a candidate only happens once, that election is unique. It has never happened before, it will never happen again. There's no way to use equally likely outcomes or long-run outcomes to determine the probability. Therefore, this probability is assigned intuitively or subjectively. In general, subjective probabilities are less reliable, but they can still be valid probabilities as long as we obey the rules of probability. Let's look at some notation. We'll use capital letters in general to denote events in a probability. For example, we'll use H to be the event of drawing a heart. If you want, you can also draw it out, like use the symbol for a heart or write out the word heart. Use P with parentheses to denote the probability of an event. So P right next to an H in parentheses which we read as the probability of H, that's the probability of getting a heart. Put the word not in front of an event to denote the opposite, that the event does not occur. So here's how we're going to introduce the rules going forward. We'll start with an example from which we can intuitively derive the solution. We'll use the solution to our example to derive a general rule, and then we'll apply the rule to another example. Keep in mind that we're going to be taking all of these and applying them to random variables and sampling distributions. Once we know how to apply these rules to random variables and sampling distributions, we'll have the tools we need to do statistical inference. So let's start with the permissible probabilities rule. Let's say that we've got a 6-sided die that we're going to roll once. What is the probability of getting a 9? What is the probability of getting something less than 9? Well, a 6-sided die only has the numbers 1 through 6 on it, and it does not have a 9. That means the probability of rolling a 9 is 0, because it is impossible to roll a 9. On the other hand, since all the numbers 1 through 6 are less than 9, the probability of rolling a number less than 9 is 1. So, the probability of an impossible event is 0. The probability of a certain event is 1. All other probabilities must be somewhere in between. For example, of these 4 numbers, which could possibly be a legitimate probability? Well, since probabilities have to be between 0 and 1, only 0.1 satisfies the rules. Let's look at another rule. The student's year is classified as first year, second year, third year, fourth year, or other. What do we get if we add up the probabilities of a randomly chosen student's year being first, second, third, fourth, and other? Since these are all of the possible outcomes, if you choose a student at random, that student must fall into exactly one of those categories. That means the probabilities must all sum to 1. So, if you consider all of the possible outcomes in a random process, as long as those outcomes do not overlap, the sum of those probabilities must be 1. So, consider this situation. A survey allows 3 responses: yes, no, or unsure. If we let Y be the outcome of a randomly chosen person having selected yes, N is a randomly chosen person selecting no, and U is for unsure, then what can we say about those 3 probabilities? Probability of yes, probability of no, and probability of unsure. Well, those are the only 3 choices, so the sum to 1 rule tells us that the sum must be 1. This is the reason why pie charts work. Now for the not rule. If a professor reports the probability of a randomly chosen student getting an A is 0.25, what is the probability of not getting an A? Well, if the probability of getting an A is 0.25, remember that's 1/4. That means 1 in 4 students get an A. But if 1 in 4 students get an A, that means the 3 other 4 must not get an A. So that means the probability of not getting an A is 0.75, which happens to be 1 minus 0.25. Another way to think of this is, since A and not A are the only possible results, either you get an A or you don't, the sum to 1 rule tells us that when we add the 2 probabilities together, we must get 1. So subtracting the probability of A from both sides gives us the probability of not A equals 1 minus the probability of A. That's the not rule. The probability of not A is 1 minus the probability of A. We can also, just algebraically rearranging that equation, express this as the probability of A is 1 minus the probability of not A. For example, if the probability of a randomly chosen American owning at least one television set is 0.98, what is the probability of a randomly chosen person not owning a television set at all? Well, that's the opposite of the situation in the background section. So not owning any TV set is the not of owning at least one TV set. So the probability is 1 minus 0.98, which is 0.02, or 2%. So let's look at the OR rule. If the professor reports the probability of a randomly chosen student getting an A is 0.25 and the probability of getting a B is 0.30, what is the probability of getting an A or a B? Well, if you interpret that 0.25 as 25 over 100 and the 0.3 as 30 over 100, then that means that 25 people out of every 100 gets an A, and 30 people out of every 100 gets a B. So that means 25 plus 30, that's 55 out of 100 get an A or a B. So the probability of A or B is the probability of A plus the probability of B. However, in order to add probabilities, we have to make sure of one thing. Here, we have a similar situation. Again, the statistics professor reports that the probability of getting an A is 0.25, and the probability of a randomly chosen student being female is 0.6. What is the probability of getting an A or being a female? Well, here again, we can interpret the 0.25 as 25 out of 100, and the 0.6 as 60 out of 100. Does that mean that the number of students out of 100 who get an A or are female is 85? Well, not necessarily, because females who got A's would be counted in both groups. So that number is too big. So when two events are considered, where the occurrence of one precludes the other, and vice versa. So if event A happens, that forces B not to happen. And when B happens, that forces A not to happen. We call those non-overlapping or mutually exclusive events. I will usually use the term mutually exclusive for this situation. When you have mutually exclusive events that are separated with an OR, you can compute the probability just by adding. In the previous example, female and getting an A will overlap, so the rule doesn't apply. We'll talk in a few minutes about how to correct this. The takeaway from this is that when you see the word OR, you know that you're going to want to add probabilities. Let's look at an example. Assuming adult male foot lengths have mean 11 and standard deviation 1.5, if we randomly sample 100 adult males, the probability of the sample mean being less than 10.7 is 0.025. The probability of it being greater than 11.3 is also 0.025. In a few chapters, we'll talk about where these numbers come from exactly. For now, just take the probabilities as they're given. What is the probability of the sample mean foot length being less than 10.7 or greater than 11.3? Well, the numbers less than 10.7 and the numbers greater than 11.3 do not overlap. So we can add the probabilities and get a result of 0.05 or 5%. Let's look at another rule. Let's say that we have a balanced coin. That means that if you toss it, getting heads, getting tails are equally likely. So we'll take our balanced coin, we'll toss it twice. What is the probability that both tosses result in tails? Notice here we're looking at an event, both resulting in tails, that's made up of two consecutive smaller events. The first one is tails, and then the second one is tails. Well, the probability is, well, the first toss will be tails about half the time. And then of that half the time, the second one will be tails about half the time. Half of a half is computed with multiplication. It gives us 0.25. Another way to think of this is to list all 4 of the possible outcomes when you toss a coin twice. We can see that of those 4 equally likely outcomes, one of them represents tossing tails twice. But just like with oars, there is a complicating factor for this rule about ands. Let's say that in a child's pocket there are 2 quarters and 2 nickels. If the child randomly picks a coin and then, without replacing the first one, picks another coin, what is the probability of both coins being quarters? Well, certainly the probability that the first coin is a quarter is 1/2, because there are 2 to choose from out of 4 possibilities. But after that first quarter is chosen, the probability of that second quarter is only 1 in 3, because there's only 1 quarter left in the pocket with 3 coins to choose from. So the second probability is not 0.5. If the outcome of the first event affects the probability of the second, then we say those events are dependent. Otherwise, if the occurrence or non-occurrence of one event does not affect the probability of a second event, we say those events are independent. If A and B are independent events, then we can find the probability of A and B by simply multiplying. When you see that word "and," you want to think multiplication. If our random process is the process of choosing a sample, sampling with replacement is independent. With replacement means after each choice, you take the one that you chose and put it back into the pool so that it can be considered again. If you sample without replacement, those choices in choosing the sample are dependent. Let's look at an application. Let's say that we want to find the probability of getting a female and then a male when we're choosing from among, first, a household of 5 people, where we're choosing 2 with replacement, and 3 of the 5 in the household are female. The second situation is the same as the first, except the choices are made without replacement. The third situation, we're also drawing without replacement, but instead of a small household, we're drawing from a large university. In the first case, we're choosing 2 people from a group of 5 with replacement. The choices are independent, because once we choose the first person, we replace them back into the pool, and they might get chosen again. So the probability that the second one is male does not depend on the outcome of the first choice. Because these are independent, we simply multiply the probabilities. The probability of a female is 0.6. That's the probability of a female. And the probability of a male is 0.4. The probability is therefore 0.24. If we choose 2 people from a set of 5 without replacement, then the probability that the second one is male depends on what happens in the first choice. If the first person chosen is a female, the probability of choosing a male is 2 out of 4. If the first person chosen is a male, the probability that the second chosen is a male is only 1 in 4. Because that number changes, these events are dependent, and so we cannot use this rule. Soon we'll talk about how we can tweak the rule a little bit for this situation. In the third case, we're choosing 2 people from thousands without replacement. Remember that the difference in the probabilities between with replacement and without replacement comes down to whether one individual can be selected twice. If we choose with replacement, that is a possibility. If we choose without replacement, it's not. Since we're only choosing 2 from a group of thousands, it's highly unlikely that we will pick the same person twice. So the probability of the first person being chosen as female is 0.6. The probability that the second person chosen as male is maybe not quite equal to 0.4, but it's going to be pretty close. So we can say that the probability is approximately 0.6 times 0.4, which is 0.24. We say that these picks are almost independent or approximately independent because the probabilities are roughly the same if the choices are made with replacement or without replacement. So how do we determine if this selection is approximately independent, if we're making a selection without replacement? Here's our rule of thumb. If the sample you're choosing is less than 1/10 the size of the population, we'll say that these are approximately independent. This is good to know because in real life, most of the samples that we take are done without replacement. So this is a computation we will do often. Take the size of the sample and multiply it by 10. That's what the 10n means here, right there. And compare that to the size of the population. As long as 10 times n is less than the size of the population, we can use this rule without worrying about dependence and independence. Here's another example. To find the probability of something occurring at least once, we can use the not rule to replace that probability with something easier. So, for example, if we're talking about tossing a coin, let's say 5 times, we can figure out the probability of getting heads at least once by using the not rule and figuring out the probability that the number of heads is less than 1 or the number of heads is 0. If I know the probability of getting 0 heads, then I can subtract from 1 to find the probability of getting at least 1 head. So the probability of heads is 1/2. Let's bump it up to 10 tosses. What is the probability that we get at least 1 head in 10 tosses? Well, the opposite of at least 1 is less than 1. And since we're counting in whole numbers, less than 1 means 0. So the probability of getting at least 1 head, that's P of A. So here A is the number of heads is greater than or equal to 1. That's equal to 1 minus the probability of not A. And not A would then therefore be the probability that the number of H's is 0. That means all 10 tosses, 10 in a row, have to be tails. The probability of that is 1/2 times 1/2 times 1/2 times 1/2, 10 times. That's 1/2 to the 10th. To 3 decimal places, that's 0.999 after we subtract. Now, certainly we could have used the OR rule because we can also interpret at least 1 as 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. And then if we consider all the different possible ways to get even just 2 heads, it could be the first 2 or the first and the third or the first and the fourth or the first and the fifth. There's so many possibilities that just rephrasing it in terms of a knot makes this question much simpler. Every time you're asked to find the probability of something, take a second and ask yourself if it will be easier or more efficient to find the probability of not A. So to recap, if events don't overlap, they are mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. If 2 events are independent, then the probability of A and B is the probability of A times the probability of B. In general, we need to find a way to use to find probabilities of things connected with ORs, even if the events are not mutually exclusive. It would also be nice to have a rule for computing AND probabilities, even if we have dependence, and we're working toward that. For now, we can look at a two-way table to consider different combinations of events when we're dealing with more than one variable. So let's look at using a two-way table. Let's say that a professor notes the gender, female or male, and grade, either A or not A, for students in the class. If we're given a two-way table that shows that set of data, where should we look to find the students who are female and who got an A? Where should we look to find the students who are female or got an A? The students who are female and got an A are the ones who are in both the female row and the A column. So that's just one cell. But to be a female, just a female, you can be anywhere in the female row. To get an A, you can be anywhere in the A column. So there are 3 cells in the two-way table that represent students who are female or who got an A. So let's move to a rule for general ORs. If the probability of getting an A is 0.25, the probability of being female is 0.6, and the probability of a randomly chosen student being both a female and getting an A is 0.15, then what is the probability of being female or getting an A? Well, the probability of being female or getting an A would be the probability of being female plus the probability of getting an A minus the probability of both. In this case, that's 0.6 plus 0.25 minus 0.15, which is 0.7. Now, why is that the right thing? Well, the reason why that's the right thing is that the 15% of students that are both are getting counted in with the 0.25 who got an A, and they're being counted in with the 0.6 that are female. Since that 0.15 is getting counted twice, we have to subtract the 0.15 out of the sum. Here's what that looks like on a two-way table. 0.6 is the proportion of students that are female. So those 2 cells together must add up to be 0.6. 0.25 is the proportion of students that got an A, so these 2 cells taken together must add to 0.25. When we add those together, we will have included the students in the A and female cell twice. So we subtract them out once, and the result is the 0.7 as we saw before. Here's our rule. If we have 2 events, A and B, the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B. Remember, when you see the word or, there's a good chance you're going to compute the probability using addition. Now it's important to know that if the events A and B are mutually exclusive, that means that if A happens, then B does not happen, which means they both cannot happen at the same time. That means that that probability of A and B on the end is equal to 0. That's why this rule and the previous OR rule that did not include the subtracted term are really the same rule. If you're only going to learn one, learn this one. Let's look at an application. For 36 countries besides the US who sent troops to Iraq, the probability of sending them early, that is by spring of 2003, was 0.42. The probability of keeping them there longer, that means they were still there in the fall of 2004, was 0.78. The probability of both was 0.33. So what was the probability of sending troops early or keeping them longer? There is a possibility of overlap here, so we need to make sure that we subtract. The probability of arriving early and staying late is the probability of arriving early plus the probability of staying late minus the probability of both. 0.42 plus 0.78 minus 0.33, that's 0.87. The other 13% of nations, therefore, had troops there for less than a year and a half. That's because they sent them after spring 2003 and they left before fall of 2004. To sum up, we looked at the definitions and notations we use for probability. We talked about different rules, including the rules for permissible probabilities, all must be between 0 and 1, the sum to 1 rule, which said that if you consider a set of non-overlapping events that make up all possible outcomes, the sum of the probabilities of those events must be 1. The not rule, which says that the probability of not A is 1 minus the probability of A. We talked about the OR rule, which tells us we use addition to find the probability of two events connected with an OR, as long as they don't overlap. And as long as our events are independent, we can find the probability of A and B by multiplying the probability of A times the probability of B. We talked about the role of replacement in sampling when we are discussing dependence and independence. And we looked at the general OR rule, how we handle it when two events overlap.